Ciao, here is a conversation with Joel Rosenfeld. Joel is an assistant professor at the University of South Florida. He has a PhD in mathematics, and his research covers, among others, machine learning, kernel methods in particular, approximation theory, and functional analysis. This time I'm a bit out of my comfort zone. Joel's research doesn't overlap a lot with my works and my studies, but I wanted to do this experiment because I'm really interested in the topics we talked about. I hope as much as you. So, after a brief introduction about career strategies and issues caused by COVID, we talked a lot about kernel functions with many digressions, such as always, statistical description of dynamical systems, relation between different spaces like Euclidean, and then more abstract ones like Hilbert, Banach. We discuss occupation kernel functions and occupation measures with applications to control theory. After that, we go on approximation of bounded and densely defined operators, but also alternative approaches when operators are discontinuous in their domain. We talked about fractional calculus, mostly about fractional Laplacian operator, but also fractional derivative, in particular Caputo derivative. There's also a part when he asked me about what I do, and it gave me the opportunity to talk about the recent work with Vahid Nateghi, which will be published at the time of this publication, I hope, which is focused on the use of kernel principal component analysis for the modeling of the thermospheric density field. Then we moved on feature spaces and methods to map back from kernel Hilbert spaces to physical space, called the pre-image problem, which appeared in our work on kernel PCA. In the end, I asked him about his YouTube channel called That Math Thing, which I invite you to visit and subscribe to. I'll put the links in the description. That's it. You'll find that sometimes I try to make some links which are not always congruent, but I hope it's at least interesting to watch me fail. You can connect with me on Twitter and LinkedIn and support us on Patreon with a monthly membership. And if you want to stay up to date, you can follow our page on LinkedIn, on Instagram, and subscribe to this YouTube channel, of course. All the links, as always, in the description.
Yeah, let's start having fun. So, could you start maybe giving us a bit of your history, both in terms of research interests, more concrete, let's say, practical steps in your career, and and the current open questions maybe, and all the strategies. I mean, I know it's a big question, but
sure.
Yeah, the strategies you're using to tackle some of these questions.
Okay, sure. So, I mean, I got my PhD at the University of Florida back in 2013. And so this was a PhD in functional analysis and operator theory. And in particular, I'm in a field called function theoretic operator theory. And so function theoretic operator theory is a brand of operator theory that looks at operators are connected to functions. So, for instance, the Leibel operator is connected to a function. We call that function a symbol of the function of the operator. So we say AF is a Leibel operator with symbol F, for instance. But my personal focus was in densely defined multiplication operators. So bounded multiplication operators are very common, and you see them pop up all over the place. So, for instance, they show up in H infinity control, and this involves the Neverland-Pick interpolation problem on, say, the Hardy space of the half plane, which is where basically the Laplace transform sends all L2 signals. And so it shows up a lot in systems theory and whatnot. But then densely defined multiplication operators also come up in quantum mechanics. So there's the Fock space, for instance. And so the Fock space basically is there's a transformation that takes you from L2, where most of the quantum mechanics happens. So you usually see the quantum harmonic oscillator, and then you can use what's called the Bargman transform to get from that L2 space to the Fock space. And when you do that, the raising operator for a quantum harmonic oscillator manifests as multiplication by Z. And so that's a multiplication operator. And it turns out that the Fock space doesn't actually have any non-constant multiplication operators that are bounded. And so you have to work with unbounded operators in that case. And so there's been a lot of characterizations of bounded operators and bounded multiplication operators, and in particular over the Hardy space that is. So my goal was to characterize densely defined multiplication operators where I could. And so there's a couple of sublet spaces where I got a complete characterization. One actually turned out to be like every densely defined multiplication operator was actually a bounded multiplication operator, which is interesting. And then I actually found a space, I made up a space where there are actually no density-defined multiplication operators, and so, or no non-constant ones. And this basically slapped together Dirichlet series with a power series, and it's very inconvenient space to work over. But that was a polylogarithmic Hardy space, and so and that was a lot of fun. So that was basically my dissertation work. And so and I mentioned this in this much detail because this directly connects to the stuff that I'm working on now. But then I graduated, and I simultaneously met my wife. And I was I was really picky about the job market, though. So in the United States, there's a lot of teaching positions, and so it would be easy to get like a visiting instructor position somewhere where you have a 4-4 load, which means you teach 4 classes in fall, 4 classes in spring, and et cetera. And I looked at that as the death of a career. I mean, like, you won't have any time to do any research. You'll just be exhausted all the time. I mean, I just taught 1 class a day. I'm pretty tired already. And I feel lame compared to my colleagues who are actually teaching like 4 classes and then trying to go on to do something. But, I just knew that the way I worked, it just wouldn't fly. So I didn't apply to a lot of those. And I was actually facing homelessness or joblessness and consequently homelessness. But then I knew that there's this whole H infinity control theory thing. I knew nothing about control theory at the time, but I knew I did, my dissertation was on multiplication operators. So I went and tracked down a control theorist, and I asked him, hey, what do I need to learn in order to get better at control theory so I can figure out how to use my tools. And after hearing my dissertation title, which was, I think, the characterization of density-defined multiplication operators over reproducible kernel Hilbert spaces or something like that. I actually don't even remember my dissertation title anymore. It's very long. He heard the reproducible kernel Hilbert spaces, and then he immediately offered me a job because him and his senior PhD student, Rishikesh Kamala Poincaré, they were working on these. They were working on this problem that appeared in a paper, and it involved reproducible kernel Hilbert spaces. They had no idea what that was or why you would care about them. And so they found somebody who knew something about reproducible kernel Hilbert spaces and just happened to walk into his door. And so they're like, oh, this is fortuitous. And then they offered me a postdoc position. And so that was with Warren E. Dixon. And I didn't know, but he's a rather famous control theorist. And so then I ended up working with him for about 4 years. And so at the 4-year mark, my wife actually got her PhD. And so we were both on the market for a position. And at that point, she was a neuroscientist. And so she does a lot of EEG work and signal processing, that sort of thing. And the idea, but I mean, this is all from a neuroscience psychology standpoint. So I mean, whereas I'm trying to train, machine learning models, she's actually trying to train an actual person. And so it's usually very simple tasks like fear and other things like that, like pairing like something with like a loud noise or something like that to get somebody to learn to react to something that's otherwise neutral. And so actually I worked with her a little bit on one of my recent papers. And so then we went on to Vanderbilt University. I got a postdoc in the Very Vital Laboratory, which is underneath the Institute for the Study of Integrated Systems, or ISIS, which was a very unfortunate name at the time.
There's a company in Delft in the Netherlands called ISIS as well, in space, that does microsatellites. So it's not so uncommon, it seems.
Yeah, when all these people came up with the name ISIS, they thought it was pretty slick, but nobody knew in the future, right? And I think there's actually, because we did a lot of defense work at ISIS, we thought maybe it would be prudent to change our name, but because it's like, DoD funds ISIS research, right? So funny. But then, so I worked there as a postdoc for a while, and then that was underneath Very Vital, which is run by Taylor T. Johnson. And then after I was there for a year as a postdoc, I was hired on as a research scientist, or a senior research scientist engineer, which is what they call you when they don't know what else to call you. And basically it was a soft money position where I was a research professor. And so I was pretty much autonomous, and basically some percentage of my time had to be working with some other people, but I was expected to go get grants and basically operate as a professor, but with no like long-term guarantees of position. And so after a year of being there, I then transitioned to where I am now, which is at the University of South Florida, where I am an assistant professor. And so I've been here since the fall of 2019. And then, as I was saying before, I was here for the fall, and then, in spring, COVID hit. And so then, basically my experience working at USF has been mostly working at home, but
are you back now? Are you back to the office or not yet?
Partially. So, I mean, a lot of my time is still spent at home. So partly because of COVID reasons, we just had a huge spike, the biggest spike we ever seen with Omicron. And so, I mean, like with teaching and stuff like that, I try to give my students as many opportunities to just stay home as they can. But I am also required to teach in person. So, so it's sort of a balance I keep trying to strike. And so, but then also during the pandemic, I set up my home office to be like a full office, because I was like basically 2 years just in there. And so now, like, so I am mostly at home, but then I come in here to teach and do some other things like this, because I also have two small children, and if we were doing this at my house, then there might be screaming and yelling, or a child just like making siren noises as they run around the house, which actually happened yesterday during a conference. So.
Okay, nice. And did you get used to it? I mean, to the pandemic, I mean, to this remote working. Do you think you adapted in a way that makes it sustainable, or is there something?
Yeah. I mean, the only thing that's missing is really communication, right? And so, I mean, as far as my own personal work, if I'm just working on my own, I mean, that's great for me. I mean, working at home, I'm comfortable. I have access to my fridge and all the other good stuff, right? But then, I mean, like, it's hard to keep in touch with graduate students. It's a lot easier to have graduate students just down the hall and like knock on their door, or they come to you. And so I think that's been the biggest thing that's been lacking, is like a solid communication with my students. I mean, we get by, and but during the first year, it's especially bad.
Right.
So that's where I am now, and right now my research is all focused on sort of operators and data-driven methods for dynamical systems, occupation kernels, and Hilbert spaces surrounding them. I mean, I consider myself more an operator theorist than a data scientist or somebody who works in dynamical systems, because all of my training was in function theoretic operator theory, and so that's
right. You're one part of the conversation on this field of application, right, in dynamical systems.
Right.
I'm more coming from the dynamical system theory, let's say, even though I'm an engineer, and but this operator's perspective sounds really appealing, and also I don't do data-driven methods, not only, at least, and but it seems the ideas underpinning these data-driven methods can be used also for normal dynamical systems. So ODEs,
sense.
So I think your perspective is much more compelling to me, to people that like aerospace engineers that know the dynamical system they're working with to some extent, and can approach it with a statistical description, with a set description. I don't know if you would agree with this definition, with a ensemble view.
I mean, the funny thing is, it's coming from operator theory. It's like it's often like a large amount of translation that goes in between, like just like terminology and things like that. So like sometimes I'll hear something and I'm not quite sure exactly what that means. But then like eventually I can, if I can repackage it into my like operator theory framework, then
And
like observables were like probably the biggest thing that confused me, because all observables are a function inside of a Hilbert space, but I mean, like, you never call it an observable in operator theory. I've never heard that before until I read like Kutz's book on DMD, and then that's where I saw that. Right. Which, by the way, I saw you interviewed both Igor Mesic and Nathan Kutz before me, and so I mean, it's what, 9 o'clock where you are now?
9:20.
Right?
Yep.
Right. So it must have been like midnight when you were talking to those guys, because they're all West Coast.
The fun one was with Gary Froyland, which is not out yet now that I'm talking, and he's in Australia, and I talked 1 a.m. I think, something like that.
Yeah.
For him it was in the morning, so it was a weird way of talking.
I gave a talk at the ETH in Zurich, and honestly, like, I mean, the first time I gave a talk there, it was like 9 a.m. for me or something like that. And it was like an afternoon seminar for them. But then they invited me again for a graduate seminar that was like, I think it was like at 9 or 10 in the morning over there, and I had to get up at 4 a.m. in the morning and give a talk at 5. That was probably the worst talk I ever gave, because I mean I was still waking up. But
Yeah.
you know, unfortunately, I mean that's the biggest problem, like with the pandemic and all. And I mean, so one nice thing about the pandemic is that, you know, I can easily give interviews like this, or I can go and give a talk at a place that I would never be able to get the opportunity to otherwise. Or, you know, if I had to fly to Zurich, I mean, that would be like, I mean, that would be a huge imposition on both me and my family, and just like getting over there would just take, and then I'd have to, but at the same time, it's just like 1 hour, you give that talk, and then everybody hangs up and there's no discussion afterwards. There's no like going to dinner and talking about things.
Yeah,
and so I didn't really get to know or talk to anybody and really do any networking that would really come with, like, you know, going and giving a talk. You know, it's sort of it feels a little one-sided sometimes, because it's like, you know, when you give a talk, I mean, you're presenting a research, you're putting the effort in order to, like, you know, carve out time to do all this. But then it doesn't seem as quite as reciprocal as it used to be, where you would also get the opportunity to meet people and talk to people about research problems. And so before the pandemic, you know, I had the opportunity to go to, say, you know, Georgia Tech and talk to some people there and get some collaboration started, you know, but unfortunately, with the pandemic as it is now, it's a lot harder to get that going. I mean, I had like a conversation for like 30 minutes with Steve Brunton, and, you know, honestly, I don't know if outside of the pandemic, if that would have been possible. I mean, it basically was a Zoom meeting for like 30 minutes, but then it's 30 minutes. What are you gonna do other than say hi, right? I mean, like, so.
Yeah. Hopefully we'll get, I don't know, we'll build some tools to allow the research community to live more better online. I don't know if the metaverse. Yeah, I'm a really big fan of a professor in Stanford working on virtual reality and augmented reality, and I don't know. I like the idea. Maybe the fact that you have a YouTube channel is pushing towards that direction. I think that we can do something online, which irrespective of the pandemic. So having extra tools. I don't know.
I mean, there are some things I feel like have helped, like conferences and stuff. Like I over the weekend was the Southeast Analysis Meeting, which is an analysis meeting that's been going on for almost 40 years over in the Southeast of the United States. Right. And so it's basically where people who do the things that I do all meet up. We do function theoretic operator theory. And it was, again, held through Zoom, like most conferences are nowadays. But there was a whole side thing, which was called Gather Town, which is kind of interesting. And where it's basically, I mean, have you ever played Stardew Valley? I mean,
no. But
no, it's like it's a little farming game on, like, you know, basically any console or computer. It's just like little 2D sprites that just walk around, have funny characters, silly costumes, etc. And that's what this Gather Town more or less is. It's like a whole bunch of these little avatars walking around, and it's interesting because you can see the other avatars in the name labels, and if you walk up to them, then it connects you to their camera. And then you have in the corner like a little Zoom like thing going on, and then when you're done with that conversation, you just walk away and you go to another one. And so then and so it was really interesting because it added like this whole social aspect that I feel is missing from conferences nowadays, right? And so I think that was really interesting. And so
was it
I think
as good as in presence?
I mean, it's still, I mean, it's better than what I had seen before. I mean, as silly as this thing worked, I mean, like it's, but then again, I mean, like, people are, it's an online thing. So everybody has their own priorities at home. And so, like, you know, somebody had like something in the oven they had to go get, or, you know, they want to go out and do something else. Whereas if you went to a conference, then everybody's just going to the restaurant and you're sitting there for like 2 hours just talking, right? And so that sort of forced interaction also breeds a lot of networking opportunities and things like that. But I mean, I think for what it is, I mean, I think the things like Gather Town probably fill that niche fairly well in the absence of being able to actually, you know, be with somebody.
Nice. Yeah. I need to look into that. So yeah, could you dig a bit into the research group itself, which is the Learning Doc? Nice name.
Yeah, sure.
Is it all made of mathematicians, or do you have computer scientists, engineers? I don't know. What's the background?
So inside the group itself, it's my own personal group, and so we have there's basically me. I have 4 graduate students. I have 2 undergrads, and I have a postdoc. 3 of my graduate students are in mathematics. 1 of my graduate students is in statistics. And then the 2 undergrads are both math. And then I have my postdoc is a mathematician who is a numerical analyst. And she was previously a postdoc with George Karniadakis. And
oh, right, okay.
And so yeah, so that's my group in of itself. But we are also we work a lot with several other groups. Like there's nonlinear controls robotics over at UF, where I did my first postdoc. That's very vital at Vanderbilt. And then there's also the systems, cognitions, and controls group over at Oklahoma State University. And with those last 2, I share a few grants. And so yeah, we work together to bring in funding and whatnot.
Right. And okay, I think it's worth. I mean, you started expanding some concepts. Maybe a question I didn't plan is can you give? I mean, when we're talking about spaces, like I don't know, similar to we have the natural numbers complex and natural real complex. So these sets, how does this Venn diagram look for the ideal spaces? We have Euclidean space, and then you mentioned Hilbert, you mentioned Fock. What's the relation?
Okay. Okay, so essentially what you're thinking of are vector spaces. And that's where you start, right? And so with Rn, you have your Euclidean space. And Rn also has this really nice thing called the dot product. Dot product allows you to define what an angle is between 2 vectors. And so then a lot of questions that so a lot of these spaces that people make are like Banach spaces and Fock spaces. These are function spaces in most cases. They're not always, but so for instance, your typical Banach space would be the space of continuous functions over, say, 0 to 1. And so, but then you could ask, if you wanted to transport this idea of or orthogonality from Rn, how would you do that for Banach spaces? You could define an L2 norm on the space of continuous functions, but that won't actually be complete in the space of continuous functions. If you try to complete your space, you actually end up getting some discontinuous functions in there. Right. And so then this whole idea of angles isn't natural to Banach spaces. And in fact, you also want something stronger than that. You want if you take the dot product with a vector with itself, then that should be the square of the norm of the vector. And so there should also be a relation between the norm of the space and this angle that's going on. And so then the space of continuous functions, you have a very natural infinity norm, right? You say, because it's a compact set 0 to 1, you can define the norm of a function as just being the supremum of the absolute value of the function evaluated over all the points in 0 to 1. And then that gives you a metric f minus g, and then super those, and then that's the distance between 2 functions f and g. Now you lose this whole Banach space structure. You lose this whole angle structure in the Banach space, and you would like to be able to get that back. And so that's where L2 comes in. And so you have something like say L2 of 0, 1 instead. And so you say, okay, well, I don't want my norm to be just the supremum. I want it to be the integral from 0 to 1 of the absolute value of the function squared. And then this becomes the square of my norm. And then there you have angles. So you have the inner product between f and g, and it gives you some number, and then that way you can think of it as sort of an angle in some abstract sense. But orthogonality is really not that abstract. It's basically you can find other functions where you take f dot with g, and if it gives you 0, then you say there's orthogonal. And then in a Hilbert space, in a separable Hilbert, you can find of orthogonal vectors where pairwise of these basis functions are orthogonal to each other and they have norm 1. And then so then you can expand your function that way, and it gives you a sort of Fourier series. And in fact, it could be the Fourier series if you choose it right. And so that's very nice. And so now you have this angle structure and all this other things. But what you lose, though, is that you no longer have functions. If you actually take the completion of this, let's say the continuous functions inside of the L2 norm, what you end up getting is you get some of these discontinuous functions, but also an integral just doesn't care about what a function does on a measure zero set. And so you have to actually define, instead of a function, you actually have to replace the function with an equivalence class of functions that differ on measure zero set. And so then whenever you're talking about the quote function from L2, you're really taking a function from an equivalence class inside of L2. And so then that means that, if you have a function in there, it's not really well defined at any sort of particular point. It's really only defined under averages. And so then you want to have something that does better. And so that's what reproducing kernel Hilbert spaces do. Reproducing kernel Hilbert space is a space of functions that is also a Hilbert space. And more than that, a reproducing kernel Hilbert space is a space where all function value, for every point in your domain, evaluation of a function at that point is a functional. So it maps the function to, say, scalars. And in fact, is a bounded functional. And that's what gives you a reproducing kernel Hilbert space. And when you have that, there's this theorem that's really nice. It's called the Reese Theorem, that says that there is a function that will basically reproduce that functional through the inner product. And so then that means that for every point in your domain, there is something that's called a kernel function that is centered at that point, where if you take a function, an arbitrary function in your reproducible kernel Hilbert space, and you inner product it against this kernel function, then you get that function evaluated at that point. And that's why we call it a reproducing kernel, because it reproduces function evaluation. And so then what's really nice is that in a reproducible kernel Hilbert space, you have this additional structure that these are actually functions. And you have that convergence in the norm of a reproducible kernel Hilbert space actually gives you pointwise convergence, or even often uniform convergence for the actual functions, and not just underneath this abstract norm. And so, and this has been used since these have been around since like 1920s, 1930s, so about 100 years or so. And it's even like shown up in, like, say, the Nyquist sampling theorem. Like it's that is basically a theorem about the Paley-Wiener space, where where all the sinc functions that you use in order to reconstruct your functions are actually kernel functions. And so, and so they basically have been present in, say, data science since the very beginning of data science. It's just they weren't called reproducing kernels back then because that name wasn't invented until 1950. So,
right, interesting. So let's say Euclidean space is the most specific one. Then we have this reproducing kernel Hilbert spaces. Then we have Hilbert spaces, and I'm missing why not all Hilbert spaces are reproducing kernel Hilbert spaces.
Well, because they have to be spaces of functions, and L2 space is a space of equivalence classes.
Right. Okay.
And so you need function evaluation to be well defined if you're going to talk about it being bounded. And so for an L2 space, there's the point evaluation isn't well defined. Right.
Okay, I see. Yeah. Okay.
And so in fact, if you look at the the Nyquist sampling theorem, basically it works over the Paley-Wiener space, which is basically a space of functions whose Fourier transforms have compact support. And so, and it's not only a space of functions, but a space of L2 functions. And so since their Fourier transform has compact support, then that means that they are actually entire functions. Because basically, if you have, there's this uncertainty sort of relation, right, between like the growth of a function or the decay of the function and its smoothness. And so the decay of the Fourier transform and the smoothness of the function. And so if you have a function's Fourier transform just is absolutely vanishingly zero outside of some bounded region, then that is the fastest decay you can have. And so that means that the original function has to be super smooth. And in this case, it gives us entire functions. And so this is an example of another function. And in a lot of cases, a reproducible kernel Hilbert space consists of either analytic functions or real analytic functions or real entire functions. And that's a very common thing. It's not necessary. There's certainly Sobolev spaces that are reproducible kernel Hilbert spaces, but you see it a lot.
Right. And so your work is focused on the use of these ideas from reproducing kernel Hilbert space, living inside reproducing kernel Hilbert spaces, applied to dynamical systems. That's a fair statement. Mostly
right now it is.
Right now.
Yeah.
Okay. Right.
Yeah. I mean, so my research has almost exclusively been on reproduced kernels. When in the start of my dissertation work, it was all about connecting multiplication operators and seeing connections with kernel spaces, and so seeing how changing the space changes the allowable operators. And so, and then during my postdoc years, a lot of it was dedicated towards approximation theory with kernel functions, and now dynamical systems. Yeah.
Right. And yeah, I had a general question about why dynamical system theory people should be interested in machine learning, and particularly kernel methods. But I guess the overall discussion could answer that. My question is why kernels and not neural networks? Let's say they are much more popular. Deep learning is fancy. It's a buzzword. Kernel maybe not less buzzword. Maybe a bit less buzzword. But
I mean, kernel was quite the buzzword back in the 1990s. I mean, when you have people like Vapnik developing support vector machines and things like that. But yeah, they sort of fell out of fashion, or at least are disguised under different names lately. I actually had a Reddit post asking, where are the kernels today? And like, I'm still sifting through all the references that people gave me. I think there was probably over 100 responses. And so people are very much still looking at this, but in the context of say data-driven methods and dynamical systems, and also operators on these systems, is that when you're working with deep learning methods, things, and your basis functions are going to be what ReLU functions, I guess, usually, and so. But the question is that what is that space that you're working over? I mean, so you're doing a lot of these like approximations, and you're trying to extract information about, say, the Koopman operator or whatever else it is. But the thing is, I mean, at the end of the day, what do operators over that space actually look like? You don't know what Koopman operators are allowed over that space. If you change the space, you change the dynamics that could be supported by a Koopman operator. So for instance, with Gaussian radial basis functions, if you look at the composition operators over that space, or the Koopman operators over that space, the only ones that are bounded operators or continuous operators are the ones that have a strictly affine symbol. And so that means that the dynamics have to be affine. They can't be generally nonlinear crazy stuff. It's literally AZ plus B. And that is the extent to which bounded Koopman operators can be analyzed with the Gaussian RBF. And so then, and boundedness is often something that's assumed. And so then you look at, all the stuff that's going on with these deep learning methods, and then you're just left to ask, okay, so you came up with all this stuff about these operators, these Koopman operators using deep learning, but what are those operators? Like, I mean, is there a rich class of these operators that can be used to approximate pretty much any dynamical system? Or does it turn out that they're mostly just trivial, and then you just happen to have hit on just the few ones? Now, there could be a totally different reason why it all works, using regression methods and all these other things, and the back propagation with deep learning methods. I do work in tomography too, so back projection and back propagation are two common things that come up in my language. But then, and so, I mean, there might be very good, say analysis or, optimization reasons why you end up with a decent model at the end of the day. But the question was about, decomposing this Koopman operator, right? And so so I don't know if there's actually any good Koopman operators over in that setting. I mean, like, because people haven't worked out general properties of the space, because every other week there's a new, deep learning method with a different space and different functions and things like that. And so then it's sort of, you don't spend a whole lot of time dwelling on that one, because everybody's always looking to the future and trying to replace it with a new algorithm, but there hasn't been like really good foundational stuff that I've seen. I could just be missing some bits out of the literature, but as far as I've been seeing it, it's basically just the assumption is that there is this operator here, and then we just use deep learning methods and regression frameworks to get at it. And that's been my impression from a lot of the deep learning methods. Whereas, my work has as an operator theorist, and even continuing in my work as characterizations and multiplication operators. Now I'm looking at characterizations of things like Liouville operators and Koopman operators over these various reproduced kernel helper spaces to try to get a sense of what kind of operators can we actually look at using these kernel methods. And because I think the kernel methods themselves are a bit superior to what you see over just general spaces, because precisely because you get this norm convergence implying pointwise convergence. Now, Igor Mezek has been very strong in telling me that there aren't necessarily invariants going to be in your space, and that is something that he has said to me both through YouTube comments and personal emails.
Yeah, I read this.
Yeah, and that's fine. I mean, so he's absolutely right. I mean, there are invariants for Koopman operators that are discontinuous, or rather not smooth. I mean, no, it's still be continuous. And the thing is that even in that case, you're not always going to be, even with time averages and all these other ergodic theory methods, you ultimately end up with an approximation of that invariant or of that eigenfunction, right? You don't actually end up with the actual one. You end up with an approximation. Right. And that's all we're trying to do with the Koopman, with the kernel methods. And the kernel methods, the game changes a little bit, where we're not necessarily assuming that we're going to have eigenfunctions of the operator. We're looking for are things that are nearly eigenvalues or eigenfunctions of the operator. So something where you can have the Koopman operator applied to phi, minus lambda phi, but that in norm is not equal to 0, but less than some fixed epsilon. And if you satisfy this less than fixed epsilon, then that norm closeness translates to pointwise or uniform closeness, which then can translate into acting very close to being an eigenfunction. And so then there's other things that you're looking for, like, so I mean, they'd be smooth the invariants, but then you start with a reproducible Hilbert space that is what is called universal. And now a universal reproducible Hilbert space basically says that if you take any continuous function over a compact set, you can get to within any tolerance you want by selecting the right function out of your reproducible Hilbert space. And so it means that you can get a close approximation, as close as you want, even up to machine precision, of these like true invariants of the Koopman operator, and that you would find using ergodic theory and L2 with the ergodic measure. But in this case, you just get a close approximation of it, and then once you have that close approximation of it, then you can still use that close approximation. And in the ergodic theory case, that's also what you can do with like data-driven methods, because you have to stop integrating eventually. You can't sum to infinity. And so at the end of the day, you also are dealing with an approximation there. And so it's the same sort of setup, and however you want to look at it. But in the case of kernel functions, you end up having this norm convergence implying pointwise or even uniform convergence. And I think that's where the extra strength of the kernel methods really come into play.
Right.
Sorry if I'm talking too fast.
No, they're really, really interesting. So I'm thinking, so it's impossible to frame ergodic theory in terms of reproducing kernel spaces. That's the limit.
It's not.
No, it's not impossible, but it's a different way of approximating the results. Yeah,
it is a different way. I mean, there can be overlap, but you have to have a whole lot of extra stuff. So I mean, like for instance, if you take a look at what happens with ergodic, is basically you're taking an observable and you're throwing in your operator over and over and over again, and such. You're throwing in the dynamics over and over again, or applying the operator over and over again, and so because ergodic theory lives in this L2 space, you're allowed to have these sort of non-smooth results coming out of it, and you could possibly have dynamics that aren't smooth, and so then what you're going to have is that and so you end up with these sort of like, pointwise almost everywhere convergence results through the Birkhoff and the von Neumann ergodic theorems. And those are, they say them positively as probability 1 results, but I also see it as you could have uncountably many points where the convergence doesn't work. But it just depends on the perspective. And but it seems unlikely that you would select a bad point, but it can happen. For instance, I mean, it should be probability 0 that we ever dealt with a rational number, but we always deal with rational numbers. It's actually the only numbers we've ever seen. And so I you know, and in analysis, you get trained to look out for like all sorts of you know, little problems like that. Like you know, you can't assume that things are going to work pointwise. Now, numerically, you have no choice. I mean, you just pick what you got and you run with it. And so with the ergodic theory way, you have to make sure that you know, basically you start with a class of functions that are proper functions, and then you look at the composition of those functions with the others, and you need to make sure you stay inside of an invariant subset of L2 of the ergodic measure that consists of maybe you say real analytic functions. And when you take the closure of real analytic functions with respect to L2 measures, with respect to measures in L2, then often you get a closure inside of the larger space. This is what happens with the Fock space, by the way. And so then you have to make sure that that operator is invariant on this closed subspace. And then if that is the case, then you can run your ergodic theorems, and then you get a stronger result than what you get with just regular one. But I mean, that's a lot of ifs and maybes and, you know, things that come in there. So then you could possibly bring some ergodic theory over to the kernel space setting, but it seems like a lot more work than what anybody really would ever want to do. So
right, I see. Okay, I'm a bit lost in the sense that, yeah, I mean, you're really high level, and but yeah, let me say I'm happy to see discussions at this level. I mean, I hope it doesn't cause confusion, and that yeah, I mean, it seems like it's enriching the conversation, trying to tackle the things from different points. I don't know if that's your same feeling.
Yeah, I mean, certainly there's a lot of value in ergodic theory. I mean, it's been around for like a century, and you know, people have gotten a lot of good results out of it. But but yeah, one thing I would say is that, you know, the kernel methods are really distinct from the ergodic methods, and the goals are slightly different.
Right.
But at the end of the day, you know, in the context of DMD, you know, we're both trying to get, both of them are trying to get, you know, approximations of these operators, and then using the spectrum of that in order to get something else out of it.
Yeah,
right.
Yeah. Okay. Can you tell me what occupation kernels are?
Okay, let's start with kernel functions. I mean, I know I briefly mentioned what kernel functions were, but so if you take a look at, say, the delta function, right? So the delta function itself is a function that maps the functions in the function space to their evaluation at 0, usually for the delta function. You shift it around, you get evaluations at different points. And so delta functions were introduced back by Heaviside back in the 1800s, and then, or I've heard somebody say it was somebody else maybe slightly beforehand, but it was around that time. And then you had people like Schwartz and Sobolev, who worked on integrating them into like a proper functional analysis framework and talk about generalized functions and taking derivatives of them and whatnot. So and so then you have these delta functions that aren't actually true functions. I mean, you know, you see them in a picture. It's like a line, you know, it's basically like a vertical line right there at the origin, and it's like just an arrow, like boom. And but you know, that's just a cartoon. That isn't actually what they are. Because I mean, like if you have twice a delta function, it gets you twice the evaluation of f at the origin, but the picture is still the same. It's still a line going to infinity. And so the idea is that you know, you can take a look at these delta functions in various spaces. So you can take a look at the delta function as a distribution on the space of C infinity test functions with compact support. And so a distribution is just a funny name for a functional. And then if you change it to the Schwartz space, which is a space of rapidly decreasing functions, which are slightly larger, which is a slightly larger space than C infinity test functions, then you call them tempered distributions. And so, and then if you get to be a slightly larger space than that, space of continuous functions that are bounded, I think that's what the space is, then you can use a Reese theorem, and then you get that additional structure out of it. And so you see that not only was it a distribution and then more structure being a tempered distribution, but now we have a larger space that has to work over, so it has even more structure. And over that space, it becomes a measure. And so then we represent the delta function as the delta measure. But you keep changing the space, and you can get different sort of manifestations of the delta function. So if you change to a reproducing kernel Hilbert space, say the Fock space, for instance, then your delta function becomes a reproducing kernel. And so then kernel functions are a function representation of the delta function that works in the setting of the Fock space, or in the setting of the reproducing kernel space that it's in, right? And so then you have this nice chain. And in particular, what they do is they represent the function of evaluation. And so the delta function being evaluation at the origin. And so then you can think of a kernel function with evaluation at the origin. So there's other functionals that we care about representing. And so if you take a trajectory, and this is for occupation kernels, and basically if you take a trajectory in Rn, and say it's a continuous trajectory, keep things simple, and then you take a space of say continuous functions over Rn, and you look at the composition of those functions with that trajectory and integrate it from 0 to t, where t is the end of that trajectory, and then that gives you a functional. It gives you a number back out of a function. That's what a function was. Now, in the space of continuous functions, you can represent bounded functionals by measures. And so there was this thing called an occupation measure, and this was by J.B. Lasserre. Well, J.B. Lasserre and Henry on, and a couple other people worked on it. I'm not exactly sure where the genesis of occupation measures came from, but they did a lot of work on it in the context of optimal control theory. Now, but the thing is, you're still dealing with a measure, and so measures aren't functions, and so it's hard to use them for, like, say, approximation frameworks and things like that. So what we did is we took that idea of this functional, and we cast it into a reproducible kernel Hilbert space to see what else we get out of it. And so if you just change the space of continuous functions to the space of, say, the Fock space or the Gaussian RBF space, then suddenly you have this bounded functional, because all you really needed for it to be a bounded functional was this continuity assumption. And so it's still a bounded functional, but on this particular space, it changes from being a measure to a function. And we call this function the occupation kernel. The kernel term because we're in the kernel space, and an occupation coming from occupation measures. And in particular, the occupation term itself, I mean, it comes from this. And so, I mean, if you take a look at this guy, this is an occupation kernel that corresponds to a spiral trajectory. And I could probably even make it a little bigger. If I try. Nope, can't make it bigger. Right. Yeah, anyway, but it corresponds to a spiral trajectory. And so you're spiraling in towards the origin. And you see that the closer you get to 0, or the origin with the spiral, you see this a mound of points building up. And so the longer you occupy a region, the larger the value of the function. And so then you think of this as being sort of the term occupation in the occupation kernel. And so this is more or less what you think of with occupation measures, is the same sort of idea. But again, it's not a function, it's a measure. So it's a bit different. And but then this nice picture gets destroyed when you take a look at the Fock space or the exponential dot product kernel, and then it just looks like a regular, like, exponential function practically. But for the Gaussian RBF, it looks like this, and it's a nice clean picture.
Right.
So, yeah.
Well, nice. You see. And this idea of densely defined. This idea of looking into densely defined. I mean, I see you challenging some, looking into dark angles in the room, like seeing whether all the operators are densely defined, or also when you said there are things that are not true for zero measure sets. So what's the practical implication? I try to read these ideas, trying to find from an engineering perspective, trying to see where this is gonna appear. And I see you mentioned a lot this example of a dynamical system with finite diverging time, like x dot equals 1 plus x squared. Is this related? And is this related? Okay,
so that's not directly related to the density definedness. And so so density definedness actually is a classical idea that goes back to the beginning of the study of operators over dynamical systems. And in fact, actually even near the inception of the kernel functions, which are partly come from things like Green's functions. And so the idea is that if you take a look at your simplest differential operator, just differentiation, and you take a look at a continuous function that's nice and bounded, say the square root of x. Now that is a function on the interval from 0 to 1 that is bounded, is continuous, but if you take its derivative, you have a pole, or at least a vertical asymptote at 0, because it's 1 over 2 square root of x, right? And so then you have, so then this operation of differentiation, it sort of gave you this sort of like discontinuity out of your function itself. But essentially, if you want to have a bounded operator, which is sort of the best kind of densely defined operator, then it should take any function in your space and send it to another function in your space, and that should always work out. So for instance, it should take square root of x and send it to another continuous function on 0, 1, right? And so, but differentiation doesn't do that. So differentiation isn't going to be bounded on that space. And so but we can still talk about a lot of things that we can differentiate that give us nice bounded continuous things, like polynomials. Like a derivative polynomial is always a polynomial back. And so, but I mean, the norm might be larger. So if you, for instance, if you take the x to the n, the sup norm on 0, 1 is 1, and because the largest point it has is at the end point 1. But then you take its derivative, and then the sup norm of the derivative is n. And so then as n gets larger and larger, you can have arbitrarily large outputs coming out. And that's sort of why we don't say it's bounded. That's exactly the sequence that tells you that differentiation is unbounded. And so the idea then is that we still would like to work with these unbounded operators, even if they are kind of a pain. And so the best thing the next best thing after bounded is going to be, say, densely defined. So that means that you can find a subset of functions inside your space that are dense inside your space, so you can approximate any function with them that you can apply your operator to. And so then this is where you look for like densely defined operators, and so then differentiation is densely defined on C01.
Right, and you're still able to work, in these spaces, dealing with this.
And then you right, and so you can talk about adjoints of these things and whatnot, and then if you take a look at these level operators and then take their adjoints, then you see that their interaction with things like the occupation kernel is well defined, and in fact is actually if the trajectory corresponds to the dynamics, then it's the adjoint acting on the occupation kernel just gives you a difference of two kernels, and which is what we use in DMD. Now. Now, your question about the finite escape time, the x dot is equal to 1 plus x squared, which gives you, say, tangent. And so no matter where you start, you're going to have a vertical asymptote happening within, say, pi time. That is more of an example of the difference between using, say, working with a pure generator versus working with a Kuban operator. So there is no well-defined Kuban operator for that dynamics. And because a Kuban operator is going to require that they actually are well defined for those points, and so basically you can have a hole in your operator, and the result of the operation of composition, because the discretization of those dynamics will end up giving you asymptotes and holes. And so,
but the generator is well defined in the domain of
but the generator is just a polynomial, right? I mean, so it's basically, you take the gradients and then you multiply by a polynomial. And that's certainly well-defined everywhere in the space. There's no holes inherent in that. Now, of course, when you try to run that, I mean, you could have some holes pop up. I mean, but the whole idea with the data-driven methods is that I would like to be able to take any data that I've observed and use that as a sample of my dynamical system. Even if it has finite escape time, I'd still like to be able to use it. And so then that's what this framework that we've been developing allows us to do. And then the finite escape time and things like that, I mean, that's all inherent in the statement for like ergodic theory, where you actually require the dynamics be forward complete, which is what allows you to make these sort of discretizations. And then when you take a look at the integrals, that come from ergodic theory, or the sums, I mean, you have to be able to apply you have to trust that your signal exists as you go off to infinity, so then you see that you have to make sure you don't have any finite escape time, because if you did, you can't actually compute those time averages. And so when we initially introduced occupation kernel, some of the reviewers came back and said, well, hey, aren't these like time averages? Like, what are you doing? And we point out that we don't require that the time go off to infinity, because if time did go off to infinity, then yeah, we'd be stuck in the same sort of setting. But when we allow it to be restricted to just 0 to t, then we can use that as just a single sample. Or if we like, we can chop it up and get more samples.
Right. I see. I see. Right.
Hope I'm coming across coherent.
Yeah, definitely. No, it's difficult for me. It's difficult. I mean, I don't know why I put myself in this situation of interviewing people I don't understand. I mean, yes, I understand why I do it.
It's admirable. I mean, it's great, and it's also quite flattering for you to reach out to us. I mean, I appreciate being invited to come and share my perspective.
Yeah, no, I mean, I do it. I mean, to be honest, I don't care if people watch it. It's just for me to have fun and talk with and have my personal lifelong conference online.
Yeah,
that's kind of the goal. So yeah, I'm sorry to the listeners and to you if I mean, let's say the fact that I publish it's a product. I just do it because it's interesting.
I'm sure other people enjoy it too.
Hopefully, yes. I mean, yes. So yeah, I'm trying to find a connection with, because I'm really interested in fractional calculus. The work you're doing on fractional calculus related to this operator theory. I'm not sure what's the best place to begin to that, because I don't know if so. I started being interested in this fractional calculus idea looking at the Fokker-Planck equation. So maybe the operator perspective appears there as well. And they said something about if you use a fractional calculus, you get the same differential equation, the same Fokker-Planck equation, but with that fractional, you are able to model fractional Brownian motion. And so you have you have memory, you have a non-finite, I mean, you have finite time correlation on the noise. And so you have this idea of memory. And then I looked back to what I was doing on DMD, dynamical decomposition in Coupon, and I said, maybe, I don't know, this is related to what they're doing on time delay embedding, because there's some kind of memory there. I don't know. You're embedding some kind of memory. So maybe that's the question. So that's the place I'm coming from. But maybe first of all, if you could give an intuitive view of fractional calculus and then get into
fractional calculus. I mean, some people say that fractional calculus started back with with the inception of calculus. Right.
Yeah. There's a letter by Leibniz. Who was it?
It was to Leibniz, and I think it was who was it? It was one of these guys, one of these other famous guys. But but yeah, it was a letter like what happens when you take the half derivative, and the only answer was like, I don't know. And then some people say this was the start of fractional calculus. I'm like, it's not really. I mean, like the answer was I don't know, and they didn't really expand on that. I think it was with Abel in the 1800s, and I think the fractional derivatives actually appeared naturally as a solution to a calculus of variations problem he was working on. I think that's where it started, but it really came into popularity with viscoelastic systems, and that was back in 1960s and 70s. And so then that's when you started seeing books being written on fractional calculus. But yeah, I mean, essentially, my perspective is that fractional calculus just provides you with another modeling framework. And so, I mean, it basically is a modeling framework that allows you to incorporate history. When you're talking about fractional calculus involving, say, Riemann-Leibel derivatives or Caputo derivatives, it's a little different when you're talking about, say, the fractional Laplacian, which is a pseudo-differential operator. But I mean, really what it is it's a certain Volterra type equation, integral equation, and it has this kernel, integral kernel, different from regular. From reproduced kernels, but it has the kernel of t minus tau raised to the q minus 1 inside, right? And that's for the Riemann-Leibel fractional integral. And so it's through that integral that you can embed history, and that's the fancy way that people like to tell it. But the real reason why people like the Caputo and the Riemann-Leibel derivatives
Right.
is that the Laplace transforms are very cogent. So I mean, like, so basically we take a Laplace transform of a dynamical system, x dot is equal to f of x. Well, that x dot just becomes s times x, assuming 0 initial conditions. And then assuming, again, 0 initial conditions, if you were to take a look at the Riemann-Leavitt or the Caputo derivatives, then both of those end up giving you s to the q, where q is a fractional derivative, right? The power of the fractional derivative. And so then suddenly, if you work in linear systems theory, you can take all those things you know about, like, stability of the systems, things like integrating the Nyquist contour and all these other things, and you can take those back to these linear systems and involve fractional derivatives. And so I think that was actually, I personally think that's why most people got really excited about them, because then you can easily involve things like delays and other things like that. And it just comes down to manipulating Laplace transforms. You never have to actually think about being a fractional derivative. It's just, another, a q in your Laplace transform. And so, that's where I think the popularity ends up coming from. Now, but it gets a lot more tricky with nonlinear systems. I mean, because there is no general, like, Laplace transform for nonlinear systems, and so it takes a bit of a different approach.
Right. But when you mentioned the Laplacian, you mean the how is it the divergence of the gradient? That's the object you're talking about, right?
Yeah. So if you have a right. So like your usual Laplacian, right? So the second derivative.
Yeah, no, because the thing is
independent variable summed up.
Yes.
Right.
Okay.
Yeah.
Because I've never worked on the Laplace transform. So, but there's
but the Laplace transform is different than Laplacian.
Okay, but is there a relation, because you mentioned them together? Are they related?
No,
it's just
they're adjacent paragraphs, but yeah, I don't mean to connect them.
Okay, sorry.
So the Laplace transform is basically like a systems theory favorite that is sort of a companion to the Fourier transform. So you think of it, the Fourier transform takes derivatives and sends it to multiplication. Laplace transform does the same thing. And just Laplace was a very prolific person, so he has a name a lot of things. So Laplacian, Laplace transform, things like that.
I see. And so fractional calculus appears in both places, let's say.
So fractional calculus for time fractional systems, it works with it has a nice intertwining with, say, Laplace transforms.
Right. Okay.
But
there's also the fractional Laplacian. The fractional
Laplacian is an operator on its own. But okay, so I guess this is where the confusing part is. So then you define the fractional Laplacian through the Fourier transform in Rn. And so so basically, so for instance, if you take the Laplacian and it takes, if you take a derivative and you look at the Fourier transform of a derivative operation, then it turns into multiplication by, I think, minus I times omega. And so then if you do two derivatives, then you end up getting minus w squared. Right. And so then the fractional Laplacian is basically defined as through the minus sign. So you move the minus sign over, and so you have minus the sum of the second derivatives, and then you take that you take the Fourier transform of that, and then when you take the Fourier transform of that, you get the magnitude of the angle squared, and then you take and then if you want to finish off that fractional Laplacian definition, you take you take that magnitude of w squared and you replace it with magnitude w to the 2 over alpha, and then you take the inverse Fourier transform, and then that finishes your fractional. But this is super important in medicine, by the way. So if you take a look at, say, the CT scanners and all that work, and so anything where you want to see, like, if somebody has a tumor or a bleed or anything else like that, you use a CT scanner with contrast or something. And so the fractional Laplacian comes up in the inversion of the radon transform, which is the data that you get through a sinogram from CT scanner. And so if you want to invert that in order to see like the actual structure that all the X-rays are passing through, you use what is called filtered back projection. And this filtering is multiplying by the magnitude of W, which is basically the 1/2 Laplacian. And so once you apply that, then
it's 2 divided by 2.
Yeah, exactly. And so then what you get is you have and so then ultimately that is used every single day in computer tomography and medicine. If anybody, I mean, like there's lines of people going into CT scanners in emergency rooms, right, to make sure that they don't have any serious injuries from concussions, or if they won't need to see like something was in somebody's arm or something like that, And so I mean, like every single day they use the fractional Laplacian in order to resolve that. They don't mention that in CT books, but I mean, like I happened to teach a tomography class not too long ago. I was like, wait, I know that operator. Yeah.
Nice. And this, by the way, sounds really similar to, before I mentioned this the color noise thing, this exponent that becomes something divided by the degree of the differentiation appears also in the Hurst exponent that measures chaos. I mean, it generalizes the definition of chaos. It seems really related to, but yeah. And you said, so you mentioned the Caputo fractional derivative. Do you use, but you also mentioned another one.
Riemann-Leibel.
Right.
Yeah.
Could you maybe expand on the difference?
Yeah, sure. So both of them involve what is called the Riemann-Leibel fractional integral. And so the Riemann-Leibel fractional integral, it basically takes any function from say 0 to t, and it multiplies it by capital T minus tau and raised to the q minus 1, and then integrates from 0 to t. And so there's actually a pole at because q is expected to be fractional, so it's between 0 and 1. So then you end up having a pole at capital T on the very right side, and so this is the fractional integral. And so if you want to define a fractional derivative, then basically what you do is you differentiate a certain number of times, and then you do a fractional integral to get you back up to that halfway point between two integers. And so that's exactly what the Caputo fractional derivative does, is that you take a function, you take n derivatives, and then you go back up one. And then that gives you the Caputo fractional derivative. The Riemann-Leibel fractional derivative is a little bit different, where basically you first integrate fractionally. So you go from, say, a 0 derivative to a minus derivative of some like power between 0 and 1, and then you differentiate an integer number of times.
Right. Okay.
And so then that gives you two different ideas, but really just it's the same operator, just in different places. But it doesn't commute, and that's the big thing. So you get different behavior out of Riemann-Leibel. And so, for instance, Riemann-Leibel fractional derivative of a constant function is not going to be 0. But since but in the Caputo case, because we take derivative first and then we integrate, well, then it is going to be 0. And so then you have this sort of relation between, you have this sort of difference between the two of them. And then this manifests when you take initial value problems between the two. The initial value problems involving Caputo fractional derivatives only require knowledge of the function evaluated at 0 at integer derivatives. So your usual physical velocity, acceleration, all that stuff comes in. And so it's because of that, it's become sort of a favorite of engineers, because I mean, there's no ambiguity there. But initial value problems with a Riemann-Leibel derivative actually involve fractional derivatives, and there's no real good physical intuition to tell you what those should be if you start with an arbitrary system. I think there has been some geometric things by like Podlubny, I think, and things like that, but I don't know if there's a generic ideas for very high order.
Right.
Yeah.
And could you get in the second case, could you get like you're measuring, I don't know, the first, second, third derivative of your system at the initial value? Can you then get the fractional derivative from observations? I think not.
No, not really.
No.
I mean, because you can have you can change any of those initial values, derivatives, and get something sensible out of it with an ordinary differential equation, right? So let's say I had like so I have like a third order system, right? And so I declare what, 0, 1, the first, second, and maybe the fifth derivative, but that those don't tell me what the third and fourth should be at 0, right?
Yeah, that's the same.
Yeah.
Okay, so there's no overarching theory above all the two ways of intending fractional calculus. So
so I mean,
when people talk about fractional calculus, they talk about both, or they imply they're talking about the Caputo one.
It depends on the context. So I mean, like some people work almost exclusively with Riemann-Leibel. I just find that when I see engineers working with fractional derivatives, it's almost always the Caputo derivative.
Okay. Because of the thing you said about you have velocity.
Yeah, initial value problems. So.
Right. Okay. And do you think this could be used? I mean, you mentioned you are mainly working on this fractional calculus for the Liouville operator, so the fractional differentiation with respect to the state. I'm not thinking about it in terms of in time. Do you think this could be used to tackle deterministic chaos? And I'm thinking, for example, the fact that I'm thinking about continuous spectrum dynamical systems. So those systems in which the spectrum of the Köppen operator is as a continuous component.
I really don't think that's going to be a good approach, because I mean, one way or the other, you're ending up with a finite rank approximation, and so then your spectrum is always going to be, no matter what you do, you're going to have a discrete spectrum coming out of your coming out of your finite rank approximation. Right? And so if you're trying to get a hold of like what a continuous, I mean, I don't know. I mean, just we don't have to appeal to fractional systems in order to see how bad this can be. I mean, I think if we take a look at the Liouville operator corresponding to the function that's constant 1, I think is that right? So then that just basically gives you, let's say in one variable. So then ultimately it takes an observable to G prime is equal to G, right? Or lambda G. And so then in the Fock space, for instance, that means that, I mean, well, and that always manifests as just the exponential function e to the lambda t. And then in the Fock space, I mean, you just have e to lambda t that's inside your Fock space, which means that you're always going to have an eigenfunction for that. And then what is the spectrum of that? Well, the spectrum of that is the entire complex plane, because any lambda works. And so then you have, I mean, what are you going to do? You take these finite rank operators, you get like 10 points, and then you say, you don't know that your dynamics is just a constant dynamics 1. Although if you were looking at your system and you didn't say, well, all these are just going in a straight line, it's kind of weird. I mean, you might be kind of slow, but I mean, let's say you don't know anything about your dynamics, then I mean, your dynamical system is that. Then I mean, you have like 20 points as your eigenvalues, and then you're like, oh, I have a great approximation of my spectrum, but truly it's the entire complex plane to be approximating.
Right.
And so.
Okay.
And so, I mean, this is also maybe where like ergodic theory might be able to shine a little bit more, because they put a lot more restrictions on their dynamics that might come into play. I don't know enough about ergodic theory to say anything.
Right.
Me personally, I have been working on a completely different approach to get convergence of a sort of quote spectra, or at least singular values. So my Rishikesh, Kamal, Poincaré, and I have recently put up on arXiv, and we submitted a paper where we basically are looking at these operators that don't map from the same space back to itself. But when you change the two spaces and say you make the image space a little bit looser than the original space, then it can accommodate that extra increase that comes in from differentiation. And in fact, if you choose the space right, you can get a compact operator out of it. And if you have a compact operator, then that means it admits a singular value decomposition. And so then what you can then do is you can say, okay, for, in this setting, I can come up with I know that I have not only a bounded operator, but I have a compact operator, and I have the singular values that are, say, going to 0. And so then in that case, you can get some sort of like, you can arrest some sort of convergence rate out of it in order to get show that your DMD routine is actually converging where it should be. And so you get a convergence of singular values. Right. And in the same setting, if you have an embedding of your domain space in the range space, then you can even have hope of finding an eigenfunction. But in general, if there are two different spaces, then you don't expect there to be an eigenfunction, because I mean, you're not going to map from this space and then get the same function back, because you might have a completely different kind of function on the other side. But if there is an embedding, then we also gave an algorithm to help find eigenvalues and eigenfunctions.
Right.
And so I don't think it'll help as far as the chaos aspect goes, because even in very simple cases we see it just sort of fall apart, and so I don't know if there's much hope there. I know that the Igor Mezek has been working on that sort of problem, but I mean, it's I don't know. I mean, ultimately, at the end of the day, all you get is an approximation, because you're always working with finite data.
Let me maybe this clarifies why I'm asking this. I was thinking again, coming from this idea of color noise, so this idea of memory. So fractional calculus embeds some kind of memory, so you have a non-Markovian system, and you map it with a linear operator, but it's still non-Markovian. And so I was thinking, if this is somehow related to time delay embedding, but even without time delay embedding. So chaos is the sensitivity to the initial condition. So if I have just the initial condition, I have no idea where I'm going. But if I have the memory, let's say if my initial condition is where I am now, where I was 10 time steps before, and again, then I can differentiate the two trajectories, even if the points are really close together now, because I can see where they were before. I don't know. This was the starting idea. I don't know if.
I mean, I honestly don't know enough about the problem to tell you if this is a good approach or not. I just don't feel that maybe. I mean, the things I'm doing with fractional systems and these occupation kernels, I don't know if that's necessarily going to be the right approach to that sort of problem. Because I mean, even speaking of history, I mean, like that's what the occupation kernels do. They embed history, and they're just like any other fractional systems do anyway. And so I mean, if you can't do it for occupation kernels with regular things, then it's probably not going to be the way forward with
Right. So you're a bit ahead in a different field, but you can see that. Okay.
Yeah.
Right. And okay. I need to decompress after this one.
Sure. So tell me, what do you do? I mean, I don't know much about you.
So I work for the European Space Agency now, but I'd like to do research full time.
Okay.
I did research before. I was in a PhD for a European network thing on basically machine learning for uncertainty quantification in dynamical systems for space debris and asteroids, near Earth objects. So aerospace engineering.
So you're working on real problems then. That's cool.
yeah, that's kind of the hope. And now I'm working for the European Space Agency again to do uncertainty propagation to compute the probability of collision between spacecraft, and then do the maneuver to optimal control. Even though now it's really not as fancy as I would like, let's say. We're just doing research, and because the thing is, there's not enough automation yet to make there's still the need for an operator to take a look at and now operator means a different thing, to look at the map between the probability of collision against the delta V, and then they need to have a discussion. So there's some kind of decision. When do we do the maneuver, when it's better? So there's more. So it's not like an optimal control problem. So there's this. But then I basically decided to do research. I have a research group that I'm funding with my salary, doing some things that came out of my PhD that I didn't finish. I left it after a couple of years. And one of the things we're doing is, so basically I'm coming from polynomial chaos expansion. That's where I started looking into functional analysis, let's say, even though I wasn't calling it functional analysis at the time. And the idea was to do uncertainty propagation. So you have a probability distribution, you want to push it forward in a deterministic dynamical system. This was the initial question. And then I also was playing with symbolic regression, genetic algorithms, and DMD, even though briefly, for data-driven methods. And I discovered Koopman, let's say. I ran into Koopman. And Koopman, I think it's promising for aerospace applications, both for uncertainty propagation and optimal control. And now I'm focusing on uncertainty propagation. So yeah, basically I have a thing that pushes forward your probability distribution analytically, instead of the need to numerically integrate and do a Monte Carlo on, or even polynomial expansion. Because I mean, the problem I run into with polynomial expansion is that when you have the Galerkin, I do intrusive one. I did intrusive one. So you have this, you do Galerkin projection on the basis. And when you do the numerical integration for each evaluation of the right-hand side, you have to evaluate the inner product between the F, the dynamics, and the basis. And you have to do that by quadrature rules. So the best I could think of is quadrature. So you have this probability space, you define quadrature points and weights, and you do a weighted sum. And then I don't know how I got into kernel methods. I think for reduced order modeling, I started with the proper orthogonal decomposition, then autoencoders, and then I kind of went back to a less. That's why I asked you about the neural network thing. I went back to this. Sure. To kernel methods that I jumped completely. I said, okay, there's PID, and then there are fancy things like autoencoders. And then in doing that, I said, okay, maybe. And in the meantime, there's this professor in MIT called Professor Linares that basically started working on the approximation of the Koopman generator for astrodynamics problems using orthogonal polynomials, so related to polynomial case expansion. And so I said, okay, can we do the same with kernel methods, which are more general, the orthogonal polynomials? And also a similar question was, can we do polynomial case expansion with kernel? And so let's say, can we use something like the kernel trick to compute this inner product? Like we have, let's say, our feature map is not an orthogonal polynomial set, but it's just a feature map. And then the f of x inner product with the basis, maybe it's some nonlinear function of the kernel of that feature map. If that's true, the inner product is analytic, and we do super quick. We push forward super quickly the probability. This is one question we're looking into. Another one is the Koopman generator approximate with kernels, which is what you're doing. But and I also had a question about this. But the difficult part for us is that we're not starting from data, so our gram matrix is not the kernel on the data, but it's the inner product of the state vector. And so we didn't manage to find a way to use the kernel trick there. And so we still need to compute this inner product with quadrature rules. And that's kind of annoying. We're a bit stuck there. So we went back to orthogonal polynomials. And then fractional calculus, I don't know. Then we got into fractional calculus because, I don't know. Because we have deterministic chaos, in particular the three-body problem in astrodynamics. And so time delay embedding sounded interesting, and I don't know. It seems fractional calculus is related.
Yeah, what you described sounds a bit like kernel PCA. Like just a bit like the problem with the gram matrix and trying to use the kernel trick there. But that is more or less what happens, right, with the kernel PCA, if I remember right. I don't use kernel PCA very often, but
even the problem. But still, you evaluate the kernel on data. Yeah. So and then you do the kernel trick, and then I had also a question about maybe related to all your work about if there's something like the the pre-image problem, that basically you have this not compressed, but this representation of the dynamics in this Hilbert space, kernel Hilbert space, reproducing kernel Hilbert space, then is there a well-defined way of coming back to physical space? Or
yeah, so I mean, like so like can you get the dynamics out of the approximation? I mean, theoretically, yeah. I mean, it shouldn't be too bad. I mean, generally speaking, what you're doing is I'm not working in feature space. I'm working on the reproduced kernel over space. So, I mean, even though features are an integral part of it, once you actually work in the function space, you don't really need to talk about features anymore. And so essentially, what I'm getting, is an approximation of this operator, AF or whatever. And let's say we're just like one dimension, so it's just multiplication by of the gradient times f, right? And so then, if you want to recover what f is, well, we have a finite rank approximation of this operator. Then try to apply it to, x. So the derivative of x is just 1, and then 1 times your dynamics is that. And so then you're approximating, as long as you have a good approximation of the operator that can be applied to the function x, then you should be able to get your dynamics back. Now, how well that'll work in practice, I mean, who knows? I mean, typically these only really work well when you have like a sort of one-dimensional submanifold of a high-dimensional space. So like when you see the the canonical example now, I think is like a flow across the cylinder, right? That's a 80,000 dimension problem because they took a PDE and that gave them fluid dynamics, but then they treat each pixel as like a whole different dimension, right? So it becomes an 80,000 dimensional system, and that should be impossible to get any sort of approximation of in general. But it works because it's really just a one-dimensional submanifold because it's a periodic thing. And so then basically if you can get a good approximation on the submanifold, then you should be able to run this for all time and it should always work. And that's what you see with the success of DMD methods there, either the stuff that I'm doing with occupation kernels or what other people are doing, which is an operator.
Right.
So yes, there is a theoretical way to get your dynamics back, but is it practical? I mean, probably.
Probably this is not related to kernel to the pre-match problem I mentioned before, right?
Yeah, as far as the grand matrices that come up in my work, all of the finite rank approximations are basically, DMD is essentially an interpolation scheme for operators. You're trying to find a finite rank operator that exactly matches what the operator, what you observed the data doing. So you basically, that it sent the observable at, gx to x1 to gx2, etc. And so what that tells you then is that the adjoint in the kernel setting is that the adjoint of the Koopman operator is sending the kernel function corresponding to x1 to the kernel function centered at x2. And so you basically have this input-output relation that you've observed for the Koopman operator when you look at it just on the adjoint, just on the kernel functions. And so then you can say, okay, well, then I know what it did to all these kernel functions. Now, let's say I want to build an operator that does this. And so then it just becomes this sort of interpolation scheme. And so, and the way you do interpolation is basically you make it a grand matrix and you invert it. And then that is basically what you're doing there. And so what we're doing is we're basically taking a look at a kernel function and we're saying, and then we want to project it back onto the span of the kernel. The image that we observe, we want to project that back onto the span of the kernel functions and etc. And we do this for the occupation kernel in the case of the label operator. But the same sort of idea. And in the label operator case, we're taking advantage of the fact that if your trajectory comes from the dynamics, then the adjoint on the occupation kernel is a difference of kernel functions. And so then that's a different interpolation scheme that we're trying to work on. And there, the projection means a lot more because in the previous case, you're basically going to get a diagonal matrix of ones because you're already in the kernel space and we're doing a projection until you get to the last mapping, which maps you to a kernel that isn't in the span of the first n minus one. And so then you basically have diagonals of one, and then you'll have one column that's all kind of funky. But with with the occupation kernel, though, we have kernel functions as the image and occupation kernels on the other side. So we have to project back onto occupation kernels, and that's where the grand matrix comes from.
Right, right.
Does that clarify?
Yeah. No, but I have again the pre-image problem coming to my head, because let's say in kernel DMD, you're still assuming that the finite rank approximation of the operator contains the state itself, contains the identity. And so you're able to come back. But what if the best approximation didn't do that? I mean, I'm not sure.
If the kernel space doesn't have
the identity,
the full state observable,
yeah.
So I mean, that's true for the Gaussian RBF, right?
Okay.
That actually doesn't have any unbounded functions, and the full state observable is an unbounded function. And in fact, you can see that just through the kernel function itself. I mean, if you take a look at f of x, then that is represented as it can be represented through the inner product as f inner product with the Gaussian kernel, and then using Cauchy-Schwarz, you get that bounded by the norm of f and times the kernel function evaluated x and x, which is just for the Gaussian is 0. Because it's x minus x there.
Right.
And so then it's e to the 0, which is 1. And so then you see that every function out of the Gaussian RBF space must be bounded by the norm by its norm. And so that means that you can't have a function like x it's being in there, because that goes to infinity as x goes to infinity. And so, but the thing is that the Gaussian RBF has this other property, and it's called universality. And so if we restrict ourselves to, say, a compact set, say the domain where we've observed everything happening, then you can get an arbitrarily close approximation of the full state observable. And then that should be sufficient as long as you restrict yourself to that domain.
Right.
Yeah, the whole game of kernel functions is universality and approximating anything you can. I mean, and that is also true for, say, support vector machines. So I mean, basically, you can approximate any sort of decision boundary using Gaussians. And so, I mean, there's also questions of overfitting and things like that, which are certainly relevant issues. But I mean, that's why you use Gaussian RBFs.
Right. Okay, I see. And so, does it ring a bell, this idea of basically computing the inner product analytically using properties of kernels? So are there good-looking dynamics for which the dynamics evaluated on the state inner product with the feature map is a function of the kernel, so that you can?
I think I just don't have a clear enough image of what you're talking about. I mean, whenever you talk about kernels, I mean, they're basically the kernel function evaluated at x and y is an analytical representation of the inner product. The inner product in little L2 for the feature maps corresponding to x and y, right? And so I mean, there is that. Now, as far as actually using a trajectory as sort of like the foundation for this inner product, I mean, I have a few ideas that worked out that we've published. Part of it is we have this higher order DMD thing where we have these trajectories as being the central object in there. And so instead of a point in Rn, you actually have an entire trajectory. It's like your point. And that's what goes on there. There's and that's the same sort of idea that goes into fractional DMD with occupation kernel Hilbert spaces. And those are more or less the same ideas, but with slightly different manifestations. But actually, I think computationally they work out the same. And that requires a bit of notions of what are called vector valued reproducing kernel Hilbert spaces, which are a little bit more abstract, but roughly the same idea as the regular reproducing kernel Hilbert space. And then there's this other one that we did, and this is for parameter identification. And so like we have this routine for parameter ID using occupation kernels and label operators. And on the face of it, it actually doesn't seem all that interesting. I mean, you basically identify these parameters by taking integrals of gradients of your observables times the dynamics, and then you integrate from 0 to t. And really what this gives you is a nice linear algebra framework in order to identify these weights. And in particular, I mean, in contrast to what you see with like the Cindy algorithm, we don't take derivatives. Like the Cindy algorithm takes a lot of numerical derivatives, and then it tries to fit the data. But in my opinion, if you're already taking derivatives, you lost, because derivatives amplify noise. So if you're taking a numerical derivative, then it's going to be a fight to get data out of it. And that's exactly what you see in the Cindy algorithm. Actually, they use a TV regularization in order to try to figure out a nice information for the derivatives. And I mean, obviously they get it to work, but I mean, but it's already a fight. I mean, like you took a numerical derivative and then you're just fighting to recover something. But if you go the other way and you do what we do, we're basically using integrals, and there's no point where we take a derivative of the trajectory. We take derivatives of observables and then we put the trajectory into those observables, but we don't actually have to do any sort of derivatives of the trajectory itself. And so what we have is this sort of natural filter, that will sort of smooth out any sort of noise that was in there. And in fact, we found that when we add things like moving averages and things like that, we actually didn't get any real improvement in the precision of our identified parameters, because we already filtered it with an integral. And so then, but
you mean adding moving averages as an additional signal to the regression problem?
So you take your data and you do a moving average filter on it to try to clean up noise or something.
Yes.
It actually didn't do anything different than what we were already doing. And so what you can see though is that so I mean, in the sense of a nice linear algebra framework, and you can identify parameters using say a more Penrose pseudo inverse, and it works out well. And if you and this more Penrose pseudo inverse gives you, say, the best parameters with respect to, say, little L2. But if you want to go the Cindy route, all you need to do is just use lasso, and then it gives you for little L1. I mean, that's basically all the Cindy algorithm is. And so then, but what's interesting in this case though is that you get there's a way to use these operators. And so we've gotten a lot of complaints where people are like, you're using these operators, but you don't need to use these operators. I mean, you can just use any sort of C infinity function and then you apply this gradient and multiply it by, and do this whole routine. You don't need Liouville operators. You don't need occupation kernels to do it. But what's really interesting though is that when you do use the occupation kernels and the Liouville operators, you end up getting that you can show that the identification of these parameters actually gives you a projection in a data-driven Hilbert space, where that data-driven Hilbert space comes from the adjoint of it's basically a Hilbert space on the symbols of the densely defined operators, which don't themselves have a norm typically, but we can put a norm on them using the occupation kernel and the trajectory we've observed. And so the whole Hilbert space lives on that trajectory, or maybe a collection of trajectories if you like. And then by actually resolving the parameter identification problem, you actually end up getting projection of your unknown dynamics F onto the span of the basis functions inside of this new inside this new Hilbert space. And so then that's the real theoretical core that I think is really interesting about that parameter ID problem. And so but when you leave out Liouville operators and you leave out occupation kernels, you miss that whole fundamental structure. And it's interesting also because it gives you a way of determining the best weights that is wholly rooted in the data that you've seen, because this whole Hilbert space is built on top of that of those observed trajectories. And so I don't know if there might be some way of trying to do this feature map or things like that. But if you're looking for an inner product that interfaces features and trajectories and things like that, it might be a direction to go.
Right.
But yeah.
And this is again compatible with fractional order systems, right? This is nonlinear system identification you're doing.
I mean, to give it away, yeah. I mean, I'm working with my postdoc to generalize it. I mean, we'll have that out in like a few weeks, actually.
Okay.
Yeah.
Okay. Okay. Yeah, I think we can. Let me show you something that I have here that I've been working last week. The Liouville operator of the two-body problem.
Oh, okay.
So that people, I don't know. I thought it was, and this was, let's say, I started doing this before thinking about contacting you, even though I contacted you months ago. So even in some
Sure,
sense,
yeah.
I was already here. Yeah, I mean, now before closing though, I'd like to ask you a brief question about why you have a YouTube channel.
Okay.
And what you're doing there, and what's the goal, what's the motivation, and yeah.
Okay. I mean, I've always been interested in doing things like art design and like Photoshop and things like that, and video editing. I've always really enjoyed that sort of thing. And you know, I mean, then you see all these like YouTubers doing fun stuff like that. I mean, I would watch it for like news, or I would watch it for like skits, you know, and all these other things. But there's like a few educational bits. Like if you look at like minute physics, and also 60 symbols, or or anything that Brady Heron does, I've really enjoyed. That always got me really like interested in trying to do something myself. And then later on came like 3 blue 1 brown, which everybody knows about, right? And I thought that would be always be a sort of fun thing to do. And so I started a YouTube channel back in 2018. I have like the worst video in the world. That's my first video there. I like super embarrassed by the production quality and everything there. But you know, I put something out there as my first video, and so I mean, it was on like the first mathematician. You know, I can't believe my brain's gone right now, but you know, like the first theorem, right? And so I thought that would be a perfect way to start a math channel, is talking about the first mathematical theorem. And so I did that, and I had fun, but then I just didn't have the time for it. I had like 2 infants in the house, and you know, like I was trying to manage, like I was a research professor at Vanderbilt, so I was more concerned with getting money and to support me for the next year. And so then I put it down for a bit. And I picked it up, you know, like when I got hired, I made a quick video on that, and then when I went to a conference, made a quick video on that, and then but it was basically all I had. But then COVID hit. And then like everybody was going online, and so I was like, man, like I mean, like, yeah, what am I going to use? I mean, like I can't do live anything at home, because I mean, my kids were like 1.5, like you know, screaming, crying from both me and my children. You know, and nobody wants to see that. You know, and like, you know, I didn't know how students were going to behave with like, you know, online things. I didn't want like my personal life to be like broadcast like all over the world. And so like if somebody takes a clip and then puts it on TikTok or something, right? So I was like, so for those personal reasons, I was like, yeah, maybe I should do something pre-recorded, because also who knows when I'll be able to actually get the time if there isn't some household emergency, especially during the beginning of the pandemic when everything was in flux. My wife had a job that wasn't like being merciful at all. They're like, you have to keep working 5 days a week, you know, 40 hours a week, and give us the hours and tell me exactly what you're doing. And I had to work around that in order to get my own work done, you know. And so I mean, now everybody's a lot more flexible with COVID, but at the time, you know, they were just like completely unsympathetic. And so then I, you know, pre-recording things when my children were asleep and like I had a moment to do something, seemed to be the way to do it. I mean, I still actually record most of my stuff when my children are taking a nap. So if it looks like I'm like a rush and like, you know, looking off at a baby monitor or something, that's probably exactly what's going on. But my kids are 4 now, so they're a little bit more well behaved. But then, yeah, so then I decided.
So you were recording lectures for university.
Yeah, for my university. So like differential equations and numerical analysis, and then later also tomography. Those were all like university classes. And so I realized that, you know, it also there was going to be this influx of people who are doing streaming videos because they don't know how to do anything else. And you're going to have Canvas being flooded with it. You're going to have Zoom flooded with it, Teams flooded with it. And within like a week, Zoom crashed. I don't know if you remember, but like in the first week, Zoom just could not handle the new load that it suddenly got. And so then it just seemed like there was a ton of instability in all the systems. And so I was like, oh man, well, if I am going to put anything together, then where am I going to put it? And well, what is the one place that has been handling, you know, a huge influx of data all the time? Well, YouTube, right? So if I just put myself on YouTube, I can guarantee that my students will be able to have access to it, you know, even no matter what device they had, and you know, and it should be readily available. And I did all the actual coursework and things like that in Canvas itself. I would just send my students to YouTube for those videos.
Right.
And so then I got a bank of differential equations videos and numerical analysis videos. I put together a bank of tomography videos and whatnot. And then, I've kept it up where some of my videos are still actually for my classes. But like, I also have more fun videos like, Tom Hiddleston getting slapped 16 times to demonstrate, fixed point iteration methods. But then like, basically at some point I realized I also wasn't having good communication with my graduate students. I wasn't able to have the nice office time where I can like scribble on the board and tell them exactly how these level operators work, how function theory works, how we can do all this stuff. So then I realized that I needed to teach them through some other medium. And so I started making this YouTube content, data-driven methods, dynamical systems, aimed specifically at my own graduate students because I wanted them to understand, what we're doing in their own research. And I figured, it could also more broadly, teach other people and, and help me meet people like you. And so then, so then I kept that up, and it's still like producing a video a week, even if I don't have a class I'm updating for. I try to put it together, and in fact, that's often nicer because I have a lot more freedom in the choice of topic. But right now I'm actually teaching a course in control theory, and one day of the week we're actually all live in person, but then another day of the week I give them one of these videos. And so I have actually split the class into two chunks where like in class I'm teaching them all about nonlinear controls, but in the online lectures I'm doing everything with linear controls but with an operator theory lead. And so it's been interesting to run these like two parallel sessions, but then I can make sure that by the end of it they get a solid understanding of how control theory works in nonlinear systems and also how control theory works for linear systems. And it gives me an opportunity to learn a lot because my training is all in nonlinear systems control. And so now I get to figure out exactly how all this stuff works for linear systems. So it's fun.
Yeah, thank you very much. I mean, I guess we can close it here. I will say this again in the introduction, but please subscribe to the That Math Thing YouTube channel. Check out the learning.group. The website is linked on the YouTube channel. Also, I guess you can find it on Google. It's been a great pleasure talking with you and meeting you in person. And not in video, let's say, in YouTube.
Yeah, sure. Live at least. Yeah.
Yes. So yeah, looking forward to your next works and your next videos.
All right. Well, thank you for having me. It's been a pleasure.